Hello everyone, I'm Yeon, Senior Director of the Logistics Research Department at Busan Port Authority. I am going to talk to you today about the eco-friendly smart port creation strategy currently implemented at the Port of Busan in response to digitalization in the global port logistics field. As you all know, due to the development of the Fourth Industrial Revolution, there are currently two major technological issues in shipping and port logistics. The first is automation technology in the field of port operations, and the second is digitalization based on information. When these two technologies are effectively combined, the functions of a true smart port can be achieved. In today's presentation, I will begin with an explanation on case studies of eco-friendly smart ports. Next, I will address the current status of the Port of Busan. And finally, I will present some promotion strategies and major projects by the Busan Port Authority. We will first look into the eco-friendly smart port cases. With the development of the Fourth Industrial Revolution technology, port automation and autonomous driving is rapidly progressing in the shipping and port sectors. First, Singapore, which is known as the world's #1 advanced port, is building the world's largest smart port through the construction of the Tuas new port. In the case of China, Shanghai Port, in order to verify the technological prowess of a state-owned company in the field of port equipment called ZPMC, and to dominate the global market, it is preemptively introducing automation and autonomous transportation equipment and vehicles to the port. The Dutch port of Rotterdam has invested in the development of automated port technology and has introduced fully automated technology with the newly constructed Maasvlakte 2 port and is currently striving to complete the smart port by developing an IoT platform and digital twin technology, which are the core of digitalization. Due to vessel enlargement, the key goals for creating smart ports in each country are to improve port productivity and efficiency, and to effectively respond to port operations in accordance with the strengthening of the Maritime Alliance, as well as to respond to strengthening environmental regulations such as reducing SOx and NOx. Currently, the world's most advanced ports have built and are operating digital-based port operation systems beyond that of only automation. Due to the Fourth Industrial Revolution technology development, smart logistics technologies, such as IoT sensors and logistics robots, are continuously being applied, and the smart port market is also growing at an average annual rate of about 25%. And among them, the digital twin market is showing a high growth rate of over 50%. Singapore Port is presented first among the overseas case studies. A plan to develop the next generation port by reclaiming the Tuas area on the outskirts of Singapore is currently underway. With a total of 65 berths, it plans to optimize vessel operations and prepare for the emergence of autonomous vessels through e-navigation technology to support safe vessel entry and departure. Port loading and unloading is planned to be implemented based on automation. Tuas Port is introducing eco-friendly technologies, not only in port operations, but also in the construction of the port. During the construction process, changes in marine ecosystems are monitored every 6 months, and in the event of issues such as pollution or ecosystem disturbance, construction is halted until these issues are resolved. Tuas Port plans to achieve zero emissions by using green electricity-based energy, rather than fossil fuels that cause air pollution. A single window-based licensing system called Digital Port Platform was developed for the efficiency of port operations, which is used for the unification of administration activities such as vessel entry, exit permit, port facility use permit, animal and plant quarantine, and crew entry-exit. The pilot Callista program has been developed to enable global cargo tracking and transportation contracts for trade companies. The second case study is the Port of Rotterdam in the Netherlands. Since the mid-90s, it has invested in the development of automated port system technology, which was finally completed in 2014 after about 20 years. As in the case of Singapore, the Port of Rotterdam reclaimed the Maasvlakte 2 area to develop a new port area and has opened a container terminal equipped with fully automated loading and unloading system that is currently in operation. The Port of Rotterdam has developed and is currently piloting the Pronto system, a monitoring platform based on IoT sensors and ship AIS, following the automated port system. The Pronto system supports the safety of ships using the port and is equipped with functions to support optimal routes and optimal fuel consumption. In addition, the Port of Rotterdam is developing a digital twin system for the safety of workers in the port and plans to operate a system that can monitor and control all port facilities, equipment, and workers in the port in real time. The next case study is the Port of Hamburg in Germany. Unlike the previous ports, it is developing and operating a smart road system that supports the optimal route and accurate arrival time of cargo vehicles entering and exiting the port while promoting automation. The system employed at the port here minimizes congestion in the port caused by the failure of freight vehicles to arrive on time due to changes in traffic conditions in the city. Now we will discuss the current status of the Port of Busan. First, due to the lack of information exchanged among logistics-related entities such as ships, terminals, and transportation companies, social problems that include various safety accidents, traffic and logistics congestion, and environmental pollution continue to occur. In particular, due to the influence of mechanization and automation, a number of safety accidents occur due to friction between working personnel, equipment, and workspace. So it is necessary to develop preventative technologies. Second, we are operating manned control-based quay wall equipment, semi-automated yard equipment, and transport equipment such as yard tractor, YT, reach stacker, RS, and top handler, TH, which are difficult to automate. In particular, as mentioned above, most terminals have a horizontal structure rather than a vertical terminal structure, which is essential for unmanned automation, so there are many difficulties in unmanned automation. Only 1 out of 7 container terminals is vertical. In addition, as the crane is retrofitted according to the size of the ship, the stability of equipment operation is low, and there are many difficult situations when switching to automation. Third, there is a limited amount of manufacturing and maintenance technology for cranes, which are the core of automation. Among the 116 container cranes in the Port of Busan, 42 were domestically manufactured, accounting for 36% of the total. Most of the cranes in Busan New Port in particular, which opened in 2006, are equipped with foreign technologies. It should be possible to directly develop automation technology tailored to the operating environments and characteristics of the port and distribute it to the site, and to perform remodeling, program updates, and maintenance immediately on site if necessary. The fourth problem is lack of source technology for essential parts. A lot of foreign technologies and products are introduced not only for cranes, but also for other core parts. The time and cost required for procurement of a product is high when crane accidents occur, making it difficult to supply and replace parts in a timely manner. In order to create a small automated port, we are required to build various support policies in direction that increases localization rates for key parts, along with localization of cargo handling equipment. The fifth problem is the high technological gap with advanced ports. The Port of Rotterdam currently operates an automated port, and the technological gap between the Port of Rotterdam and the Port of Busan is large due to the lack of awareness and related legal systems, as well as low labor market flexibility of existing terminal workers for job transition. The last problem is the lack of interest in policy support for the development of new technologies for smart logistics, not only at the ports, but also at the logistics centers located in the port hinterland. Amazon's anticipatory shipping is a good example, which collects customer purchase data with IoT technology, analyzes it using big data and AI, determines the expected purchase item and time, and secures inventory in advance and manage the logistics center in a way that allows immediate delivery upon purchase and payment. However, there is currently no Smart Logistics Center function in the Port of Busan, and due to the nature of shipping in port logistics, it is only concentrating on mass transportation and storage. I will now explain the promotion strategies and projects in the Port of Busan. We will focus on various projects to solve the problems that were mentioned earlier. The first project is to build a digital twin platform for the Port of Busan. We are currently carrying out the first phase of the pilot test with government support, and the establishment of the test platform will be completed by the end of this year. The productivity of container terminals was the focus in the past, as shown in the figure. The digital twin platform of the Port of Busan is encompassing 3 phases: ship and cargo entry, exit optimization, container terminal optimization, and hinterland logistics and transportation optimization. In this slide, we will look at the development of smart logistics core technologies. The project consists of 3 main tasks. First, the development of a system for the safety of workers in the port, along with the localization of core sensors for autonomous transport equipment. Second, the development of automation modules and technology for forklifts used in logistics centers. Third, the development of a tracking and control system. This project will be developed with the support of the Korean government and the city of Busan for 5 years, with an estimated budget of $12 million. The development will be completed in 2022, with plans to expand the market domestically and internationally by 2024. This is a promotion project for domestic production of port loading and unloading equipment. We are supporting the local production of cargo handling equipment and securing core technology together with Korean heavy industry companies. In particular, BPA is in the process of having Korean companies manufacture 55 cranes to be introduced in phases 2-5 of the West Container Terminal, and plans to introduce more cranes manufactured by domestic companies to container terminals to be developed in the future. The economic effect is expected to be about $860 million, which is 3 times more than the $258 million invested in Phase 2-5. We are developing the technology for key parts of port handling equipment. The program conducts a full investigation of all cranes in the Port of Busan, identifies the core parts into 2 groups, which are mechanical and electrical parts, and converts the parts that depend on foreign technology to domestic technology. Currently, we are developing 3 core technologies: spreader, cable reel, and crane predictive diagnosis system. This year, we plan to develop inverter, emergency brake, and automated stop technology. The Port of Busan's ultimate goal is to achieve over 85% localization of key parts for port cranes, which currently stands at 30%. We will now look into the BPA 300 project, which is a plan to foster 300 SMEs related to ports. As mentioned previously, we plan to invest in joint investment with 300 startups that will be in charge of developing core parts for port cranes and smart port technology, conducting R&D, and selling products domestically and internationally. We are currently building a startup center that will become a base for growth for 300 startups. The 4-story building is being built in the North Port redevelopment site behind Busan Station, and it is scheduled to open at the end of September this year. We plan to expand the development of new technologies in smart ports by fostering startups in the port sector. In this slide here, we will take a look at the development of core technologies for autonomous driving transport equipment. We are developing a technology to convert yard tractors, which are mainly used in horizontal terminals, to autonomous vehicles. Currently, about 700 yard tractors are in operation in the Port of Busan, and we plan to complete the development of the core parts for autonomous cooperative driving and operation technology in the port by 2024 and supply them to the site. We are developing remote control technology for port cranes using 5G technology. Mobile edge computing technology is being linked with 5G technology, and development is expected to be completed next year. This technology will secure transfers of large amounts of data faster and more accurately. Currently, it is applied to transfer cranes, which are yard equipment, but it is planned to be applied to container cranes and transport equipment in the second phase. We plan to establish a joint smart logistics center. The Korean government and BPA plan to jointly invest and build a fully automated logistics center with smart logistics technology, which differs from a conventional logistics center in the port hinterland. We also aim to make cargo stevedoring and transport and logistics management center smarter with new technologies. Furthermore, we are developing a resource-sharing platform for the Port of Busan. In line with the concept of sharing economy, we are developing a system that enables to share facilities and equipment in container terminals during their idle periods. The platform development is expected to be completed this year, and it is planned to expand not only to port facilities and equipment, but also to crane parts procurement and maintenance. Lastly, I will introduce the plan to create a green hydrogen port. In relation to BPA's ESG management system, we plan to develop and apply hydrogen-related technologies, which are eco-friendly, in order to reduce fine dust generated in the Port of Busan. We plan to promote the conversion of all transport equipment to hydrogen, energy independent, through the installation of hydrogen power plants in the port, and establishment of a base for importing and exporting hydrogen energy. The last slide here displays the Smart Port of Busan in 2040. You can look forward to seeing the Port of Busan with all the fourth industrial revolution technologies applied. This is the end of the presentation. Thank you for your time.